Hi all, welcome back to Malware Analysis. I am J. Lavanya, Assistant Professor of CS2 Department. Today in this video, we are going to discuss on the Unit 4, it is the topic Build and Debug the Malware. Under this particular unit, we are going to discuss the subtopic called Low-Level Language Registers, Memory Addressing, and Opcode bytes. Okay, so let's dive into the topic. First of all, low-level language registers memory addressing and opcode bytes. Why is it needed in the malware analysis? So, in malware analysis, if you take, so here understanding this low-level language like register, memory addressing, and opcode bytes, it's crucial for reverse engineering and comprehending some malicious functionality. Okay, and also if you take here, this is the low-level programming concepts in malware analysis. First of all, in malware analysis, like understanding the malicious, software or behavior, we have to turn it out. And here in this opcode bytes too, we have like instructions for executing. The operations is called as opcode bytes, and for locating the data in memory we used to call as a memory addressing, and for storing the units for immediate data access we used to call as register. So all these terms, if you have learned the microprocessor in the architecture, in that particular subject also they'll be dealing with these kind of the terms like opcode bytes, memory addressing, registers, right? I think you might have just gone through. So all these terms similar to that in microprocessor and computer architecture, we will discuss here in terms of malware analysis and how to build and debugging the concept of malware it is used, right? Okay, so first topic is that registers. So registers are a small high-speed storage locations within the CPU that hold the data and the instructions actively being processed. And this malware often manipulates registers to control the program flow, store the temporary values, or access some specific memory locations. And also, for example, if you take like EAX register, that is commonly used as an accumulator for the calculation purpose. And here, this ESP points to the top of the stack, and EIP holds the address of the next instructions to be executed. And this malware can modify the EIP to redirect the execution to the malicious code. And this malware often manipulates the registers to store some temporary values like decrypting the code or the keys, and set up the parameters for the API calls like on x86, often in registers or on the stack, and control program flow by manipulating some EIP or RIP instructions pointer. Okay, so by means of these, the registers can be manipulated in terms of software, right? And here you could see a small example for this register, like move, that is move eax comma ebp plus 8, and next segment like call eax. So the first, that is the line denotes we are loading the function arguments into the eax register, and next we are calling the eax. So once we have loaded this particular value to this register, that is ebp plus 8, and again we are going for some indirect call, right? Like execution may jump to some malicious code. So this what we used to call as a small example. And what does mean by, right? Like there will be some terms of registers where we using, like what does mean by EAX register, right? So this EAX register, this stand for accumulated register is used for some input port access or arithmetic or some interpreted calls. Okay, so that is what EAX and EVP register also, that uh, it stands for like the base pointer, like the register containing the address of the bottom of the stack frame instruction pointer, and register containing the address and of the instructions to be executed, right? So this is what, and if you're calling this EAX, it will be going to some malicious code or it may not, right? Like based on the a program or the instructions you're passing, it will be manipulated. Okay. And the next topic is that we're gonna discuss on the types of registers. Okay. So this is a very important topic in terms of registers in malware. So the first topic is that these are like general types like general purpose register, segment register, instruction pointer or program counter, and stack pointer, base pointer, or frame form pointer, and next one like flag register. So first topic, that is general purpose register. So these register like example EAX, EBX, ECX, EDX, like in x86 or architecture, or X0 or X30 in ARM architecture. These are used for some various operations, like including some arithmetic or logical operations and some memory addressing. Okay, and segment register. So in segmented memory architecture, like less common, just commonly used today. So these register like example like CS, DS, SS, ES, FS, GS in x86 define the starting addresses of the memory segments. And third one like instruction pointer or the program counter. So this register holds the address of the next instruction to be executed. So modifying this register is a common technique that is used in control flow hijacking, right? And next one like stack pointer. So this register points to the top of the stack, a region of memory that is used for storing some temporary data and function call information and local variables. And next one, that is the base pointer or the frame pointer. So this register points to the base of the current stack frame, facilitating access to some functional arguments and local variables. Okay, and next is that flag register. So this register contains the status of the flag that reflect the results of some arithmetic as well as some logical operations. Example, zero flag, carry flag, over flag. Okay, so these flags that's used for some conditional branching. So when you're writing the code, you'll be using these kind of registers for storing, or if you want to go for some temporary allocation, or like want access from the current stack frame to the next stack frame, right? And what type of instruction will be executed on the next step, all for these kind of stuff, right? We're gonna use these type of register. Okay, the next topic, how this registered usage in malware. So malware often manipulates the registers to perform some very malicious activity. The first one, how it is used and how it is data manipulation. Okay, so this data manipulation, a malware uses some general purpose register, right? So general purpose register, like EAX, EBX, ECX, right? So that type of register we use for data manipulation to perform some arithmetic and logical operations on the data, such as encrypting data for ransomware or modifying some system settings. Okay. And second one, like memory addressing. So this register are used to calculate the memory addresses, allowing some malware to read and write to some arbitrary locations in memory. Okay. And third one, like control flow hijacking. malware can overwrite the instruction pointer, redirect the execution to some malicious code. Okay, and apart from that, also this is a common technique in buffer overflow exploits. Like, and next one, like function call, if you take. So this function call, malware uses some register to pass the arguments to functions and to store some written values. Okay, understanding like these type of calling convention is crucial for the reverse engineering malware. Right, and next one, like anti-analysis. Malware may use some register manipulation to obfuscate its behavior and make it harder to analyze. For example, it might use some register-based calculations to determine the address of a function to call rather than directly calling the function. Okay, so this is all the register usage in malware. Okay, and next one, like memory addressing, right? So this memory addressing refers to how the CPU accesses data stored in the memory, and the malware utilizes some various addressing modes to interact with the memory, including like direct addressing, like register addressing, and third one like indirect addressing, and fourth one like base index addressing. So first of all, this is direct addressing. So here is instruction directly specifies the memory address of the operand, and this register addressing, the operand is located in a register. And third one, like indirect addressing, this instruction specifies a register that contains the memory address of the operand. Okay, and fourth one, like base index addressing, the address is calculated by adding a base register, an index register, and a displacement. So this, malware frequently uses these type of modes to read or write data and access some specific API functions or inject code into the other processes. And this malware frequently uses some indirect memory addressing to hide what it's doing. Like indirect memory address, you can't able to say where it's gonna store or how it is going to use by the programmer, all those stuff, right? And next topic, like Excel used, like how it is hidden, please, and that we will discuss. So the first topic is that like pointer chasing, right? In terms of pointer chasing, if you take this pointer chasing map stores the function pointers in the memory, then resolves them at runtime. And it's like self-modifying code, which writes the bytes into the memory and later it executes them. Okay. And next, like code injection, it writes the payload to the memory. That is a write process memory we used to say, and then it executes it. So that is uh, it is used like indirect memory addressing, like pointer tracing, self-modifying code, and then code injection. Okay, so this is the example of the memory addressing. Like so, like in previous example, we have discussed like for registers. So same as the case here also, move that is MOVEAX. So the base register and comma EBX plus 0 into 10. So here this gets the function pointer from the memory table. Okay, and then like call EAX. So jump into the function. Maybe it can be an API like load library A. Okay, so this is an example for the memory addressing. Okay, and the next topic is that memory addressing in malware. But before going to this, I would like to state how it will be stored in the memory organization, like based on some a linear address space that modern operating systems typically use a linear address space where each memory location has a unique address. And second one, like virtual memory, operating systems use some virtual memory to provide each process with its own isolated address space, and this prevents the malware from difficulty accessing memory belonging to other processes or the operating system kernel. Okay, and next one, like memory segmentation. In segmented memory architecture, a memory is divided into segments, so each with a base address and a limit. Segment registers are used to specify the current segment. And next one, like a paging, virtual memory are typically, implemented where the virtual address space is divided into some fixed size pages. The operating system maps the virtual pages to some physical pages in the RAM. Okay, and addressing mode in terms of here, it has like direct addressing, like the address of the operand is directly specified in the instruction. And second one, like register addressing, the operand is located in the register. And third one, indirect addressing, the instruction specifies a register that contains the address of the operand. And next one, base plus offset addressing, the instruction specifies where it's calculated by adding an offset to the value in a base register. Okay, and next one, like indexed addressing, the address of the operand is calculated by adding an index register to a base address. Okay, sorry. Now we are going to discuss this about memory addressing in malware. Okay, first topic, how this malware uses the memory addressing. Okay, okay, the first one, read and write data. So here the malware reads some sensitive data from the memory, such as passwords, credit card numbers, and encryption keys. It also writes the data to the memory to modify the system settings or inject the code or override some files. And second one, the code injection. This malware injects the malicious code into other processes by writing the code to a specific memory location and then redirecting the execution to that location. Okay, and third one, like heap spraying. So this malware allocates the large blocks of memory on the heap and fills them with the malicious code or the data. So this increases the likelihood that a vulnerability will override a written address with an address within the sprayed memory. Okay. The next one, return oriented programming, that we used to call ROP. The malware chains together small snippets of code, its gadgets that end in a written instruction. So by carefully crafting the stack, malware can control the execution flow and perform some arbitrary operations. Okay, so these all comes under the malware addressing. Okay. The next topic we are gonna discuss is that opcode bytes. So this opcode bytes or the mission code instructions that the CPU directly executes. So each opcode corresponds to a specific operations. Example, MOV for move, ADD for addition, JMP for jump. Okay, so all these kind of like acronym or the short terms you would have seen in computer architecture and microprocessor subject, right? So you can just brush that particular subjects. Okay. And next is that malware analysis. Examine the code sequences to understand the program's logic and identify the malicious patterns. For instance, a sequence of opcodes might reveal a shellcode injection, anti-analysis techniques, or data exfiltration routines. Okay. So disassemblers translate these opcode bytes into some human readable assembly language mnemonics for some easier analysis. Okay, so these are some instruction components that is used in opcode. Okay, so first is that the opcode. This specifies the operation to be performed, and mode R or slash M byte so specifies the addressing mode and the registers in the x86 architecture, and displacement so offset added to a base address for a memory access. Okay, and next like operand specifier, this indicates the operands to be used by the particular instruction, and SIB byte used for some scale index addressing in x86 architecture. And next, like immediate value, this is instruction a constant value which is used as an operand. Okay, so these are the basic instruction components which is used in opcode. And next one, like opcode bytes, small example. So here you could see like there is some um, it's like hex terms which is used like ultimately like code bytes you are going to write get while you are decoding. So analysts often look at some hex stubs, or assembly to see some patterns. So these like EB10, 5B31, C0, 50, 53BB, all these like hex terms. Once if you're decoding like EB10, they'll be jumped to short plus 0 into 10, that is jump forward. And 5B, it here represents pop, EBX, okay. And then 31CO, XOREAX, comma EAX, that is zeroing the EAX value. So all these, you're decoding, you'll be getting some kind of registers, okay, that's used for some memory addressing or for instruction purpose, okay. So this opcode byte, typically consists of some opcode and specifies the operation to be performed, like example add, subtract, move. And second one like operand specifier, which indicates the operands to be used by the instruction. Example like register, memory addresses, and immediate value. And next like mod or mod m byte. Here in x86 architecture, right? Uh, this part specifies the addressing mode and registers to be used. Okay, and next like SIB byte in x86 architecture. So this byte is used for some scale index addressing, and next like displacement and offset added to a base address to calculate the final memory address. Okay, and this immediate value, if we take a constant value which is used as an operand. Okay, so this is a small example, and next one is opcode bytes, how it is used in a malware. So malware uses the opcode bytes to execute the malicious code, obfuscation, shellcode, packing and unpacking, and then anti-disassembly. So execute the malicious code. So the malware consists of a sequence of opcode bytes that perform some malicious actions. So this second one, like obfuscation, a malware may use some various techniques to obfuscate its opcode bytes, such as encryption, polymorphism, and metamorphism. Okay, and next, like shellcode, if you take this shellcode is a small piece of code which is typically written in some assembly language that is used to exploit the vulnerabilities, and this shellcode often consists of opcode bytes that perform actions such as opening a shell, downloading a file, or injecting the code. And next, like packing and unpacking, malware may be packed or compressed to make it harder to analyze. The unpacking routine, which consists of opcode bytes that decompress the malware and restore it to its original form. And next one, anti-disassembly. This malware may use techniques to confuse some disassemblers and make it harder to understand the code. And this can involve inserting some invalid opcode bytes or using some instructions that have some different meanings depending on the context. Okay, and this opcode bytes or the raw binary instructions of a CPU that executes. In malware, they often use some few key purposes like first, like evasion and direct system interaction. In evasion, the malware authors can use some low-level assembly to write highly customized and obfuscated code. And this makes it difficult for some security products that rely on some signature-based deduction, as the malicious opcodes can be unique to each variant. Techniques like metamorphism and polymorphism involve rewriting the malware's opcode sequence to create new, slightly different versions of the same malware, each with a different signature. So this makes it much harder for any antivirus software to identify and block. Okay, and next, like direct system interaction, rather than using some like high level programming language like Java or something high version of Java, all those stuff. It's used to monitor by security software. Malware can directly use some opcodes to perform some low level tasks such as making some system calls, and this allows it to interact with the operating system kernel, allocate the memory, or communicate over the network without being detected by some security products that hook into some user mode API. Okay, so these all comes under the direct system interaction, and there are some real-time, cases where this is applied. Okay, if there is a manual author, he's writing some code in a high level language. Say like in C is equal to 5, C is plus 10, or something like. So once it goes into the compiler, it will be turned into a mission CPU code. Okay, so there like it will be in a hex format like B7, B645, 3D, all those stuff. And one again it passes to the disassembler. So there the malware analyst, what he will do is he will be using these kind of register like start move EAX to 0x4, move EBX comma 1. He will be writing. Okay, so for these kind of stuff, so mainly like 32-bit or 64-bit. If you go for some 32-bit architecture, you have to go for some x86 and x86 assembly language you have to use. So while you're using these kind of thing, it will be manipulated, it will be automatically saved. For example, uh, for each and every register, if I'm choosing like Ubuntu, like 16.0 for 64-bit, okay. First, you have to install the NASM. So, and then you have to write the test code, right? The data section, you have to write the start, move, EX, and exit section, base section, a text section, BS section. Okay, that will be so many section. So, while you're compiling this program, it will be executed and it will be showing some sort of uh, hex code. Okay, so there will be no output over there, and by means of there, you have to just go for the assembly section to execute, or for point of view in terms of malware analysis, you have to use some obj dump. Okay, that command is very important. You have knowledge for static analysis. Okay, so this static analysis is a process of analyzing the malware address to extract some identifying features and other characteristics from the tool without actually executing it. And this obj dump, what it will do is that it's a part of some util package, which is a bundle of tools which is used in Linux, Unix system for working with many core binary file types. And the obj dump utility is designed to be a full metadata analysis and reporting tool for some executable files. So using the minus D arguments, obj dump can be told to disassemble the file. Okay, say like move ex comma 1, there it will be executed, and move ex comma 0. Okay, so what will happen here, it will be just a system execute will be calling the system call, and second it will be calling the system exit. Okay, so thereby you can just go for some redirect option and all those stuff, right? So in addition to that, we can able to use some strings also. So that isn't a very advanced concept, but as of now, you can just know the basics of register opcode, how it is used in malware. Like if you are going for some advanced beta version, by loading some binary to the GDB, for testing the file, you have to give some breakpoint and some reading the symbols for test cases and for the exit section and all those registers as well as for the code. Okay, so this you have to practice. Then only you can able to see how this particular code is working on. Okay, so that's all for this session. And so I just want to summarize. In this session, we have discussed on the low-level languages like register, memory addressing, and opcode bytes, right? In register, we have discussed the types of register and how the register usage of register in the malware. And next, like memory addressing, we have discussed so many like direct register, like yeah, and how the addressing modes is used. Okay, and same as that in opcode bytes too, we have discussed about how the simple example and how this opcode byte typically has something and how it is used in malware, right? So these are the topics we have covered in this particular thing, in this video. So hope in the next video we will see with different topic. Thank you all.